So what we want to do today is this, layered medium. So here, as I mentioned earlier, we have incident wave, okay? Incident wave of angle of incidence theta I. And then of course, theta R should be equal to theta I, right? That's what we know from the previous examples. And then by applying Snell's law, we can also determine theta 2, right? And here also theta 2, and then by applying another Snell's law, we can obtain theta t, right? So once we determine theta I, once theta I is given, all the other angles are just determined. It's not a variable, it's just a determined value, okay? And then same thing applies for like multiple reflections, right? It's just the angles are the same. So we can easily determine the wave vector of each partial wave. So here we use subscript I for incident wave, and then subscript R for reflected wave, and subscript T for transmitted wave. And then here in the medium 2, we have forward propagating mode and the backward propagating mode, and these are called K2 plus, K2 minus. Okay, so we have 5 wave vectors. And then by applying Snell's law, the relation between theta I, theta 2, theta t are just fixed, right? We know the relation. Okay, so one way to solve this problem is this. Like, because we know the incident wave, the incident wave should look like this, right? Ki r, and then this is ei naught, which is the incident wave amplitude, and then reflected wave, which is this. So this is the electric field in medium 1, the total electric field in medium 1. H, once you know E, then you can get H. There's no ambiguation, right? So this is your H1, Hi, this is your HR. So this is basically, these are the electromagnetic fields, total electromagnetic fields in medium 1. And similarly in medium 2, you have plus mode and minus mode. So that's 2. And then in medium 3, there only is a transmitted wave, right? So how to solve this problem? Well, that's easy because you know the boundary conditions. When z equals 0, that's the boundary 1, medium boundary between 1 and 2. And then when z equals L, right? If you go back to the previous one, L is the second boundary. So if z equals L means this boundary condition. Okay. Now we know that you have 4 unknowns like ER naught, E2 plus, E2 minus, and then ET naught, 4 unknowns, right? And then you have 4 boundary conditions. So you can solve it. 4 boundary conditions, 4 unknowns. If you make an equation, you get the solution. So that's, and then once you do it, and then taking the ratio between the reflected wave and the incident wave, you get the reflection coefficient. And then transmitted wave and incident wave, you get the transmission coefficient. Okay, so this is approach 1, right? And here, the biggest thing is that you consider all these waves, like you have many partial reflections, right? Like undergoes reflection again and again and again and again. But you just, because all these waves have the same k vector of kr, so you just decide to describe things like er naught e to the minus I kr dot r, right? And then this thing takes into account all partial waves, right? That's how we simplify the problem. And there's no problem doing this because anyway, all these things share the same k vector. And then the second method is this, okay? And here the second method is just assumes you know the reflection and transmission coefficients at each boundary, okay? And in this case, what we do is we set like, at first interface, EI naught coming in, and then you obtain EI naught multiplied by gamma 1, 2. Gamma 1, 2 is the reflection coefficient of this interface. And then you have tau 1, 2, which is the transmission coefficient. And then this wave propagates, right? Actually, it propagates along this way, but because a plane wave is just infinitely wide, so you can always calculate the wave propagation, effective wave propagation length is actually this amount. E to the, so same as this, the same amplitude, e to the minus jk2d. D is L cosine theta, right? So this is L cosine. And the cosine theta coming from, so from here to here, it's L. And then cosine theta is coming from the angle between the k vector, k2 vector, and the propagation direction, right? So you remember the second wave is e to the minus j k 2 plus dot r, right? And then when r is like basically 0, 0, L, then it's only have z direction, whereas K2 plus have both z and x direction. So if you take a dot product, what you need to do is you need to do L cosine theta, right? And then at this boundary, there's another reflection coming in, and the transmission occurs. So now you multiply t tau 2, 3 to this term, right? 2, 3 to this term. And then this wave is reflected. So after reflection, you need to multiply gamma 2, 3, right? Gamma 2, 3. And then here, when this wave arrives at this boundary, you need to take into account the propagation. So now you're propagating twice, right? 2 times, so you need 2 here. And then after it arrives here, there's another transmission, which is tau 2, 1. And then another reflection, gamma 2, 1. And so on and so forth, going forever, right? So now you can think of adding all these terms. So you have gamma here, which is the ratio between the actual reflection, like reflected wave amplitude to the electric field incident wave amplitude. And here it takes account, you can see here gamma 1, 2, right? And the second one is this. So second one is tau 2, 1, tau 1, 2, gamma 2, 3, e to the minus 2 jkd. So that's that, right? And from here, what's happening is that what's coming out here actually requires one more reflection at this boundary, right? And then one more reflection at that boundary. And then same transmission, like this transmission and this transmission are same. So what it actually have is one more reflection at this boundary and one more reflection at that boundary and two more propagation. So one more reflection, 2, 3, and another reflection, 2, 1, and two propagation, e to the minus 2j kd. And then that goes forever, right? So these forms 등비수열. I'm not sure what 등비수열 is in English. What's 등비수열? The series, like, you know, so 1 plus a squared plus a cubed plus and so on. This is in Korean called 등비수열. I'm not sure what's it called in English. But anyway, you got the point. Once you okay, geometric sequence. Good. Thank you. So yeah, so once you have a geometric sequence, then you can easily obtain the sum of a geometric sequence, infinite geometric sequence, by just taking 1 minus this a, right? So that if you do this, you get the answer, right? So assuming that you know all the reflection and transmission coefficients, you can easily obtain gamma. And similarly, for tau, so the first transmission is this. So tau 1, 2, tau 2, 3, and then one propagation. And then after this, the difference between the first component and the second component is that the second component have one more reflection here, and then another reflection here, and two more propagation, right? So one more reflection, 2, 3, and another reflection, 2, 1, and then two propagation, e to the 2 jk to d. And this also forms infinite geometric sequence. And then if you have, and the solution to this is easy. This is how you obtain the reflection and transmission property for a layered medium. Okay. But of course, as you realize here, this method is already a little bit too complicated, right? So assuming that if somebody asks you to obtain the transmission and reflection for double layer material, double layer thin slab, then you ended up having 3 interfaces, then the problem becomes like infinitely complicated, right? So this approach is good and intuitive for a single layer medium, like when you have just 2 boundaries. But as the boundary number increases, this approach becomes increasingly more difficult. And you ended up better doing something like this. Okay, and then of course there are ways to generalize things. So like you can make a matrix for each. So generalized way of doing this is that you have a reflection matrix. So you can create, say, here's the input wave. So here's the input wave, and then so here, yeah, input electric field. Here's the output electric field, and here's the wave components. So matrix components, and then here's the output, like E, here 2 plus, E 2 minus, something like this. And that only takes into account the reflection and transmission at the interface. And then the propagation can be taken into account another matrix. So when it's forward propagating, when it's the forward propagating mode, then as you go from here to there, you have e to the minus j k to d phase advance. And when it's a backward propagating mode, but you go from 0 to L, you actually, your phase change is actually plus jk to d. Okay. And then here is the electric field at this position. And then at here, we also have a matrix taking into account the reflection and transmission, and so on and so forth. So this way of solving the problem is called transfer matrix. Transfer matrix formalism. And then once you have a transfer matrix for all the interfaces and the bulk, you can deal with arbitrary number of layers without too much of a problem. Okay, but this is beyond the scope of our lecture at this moment. So, but similar problem actually is introduced in the in homework. So you can just have a look. Yeah. So this is it. So if I recall what we learned so far, this is kind of grand summary of everything. So we begin with mathematics, right? We learned about this del operator and then integration and so on, meaning of these things. And second, we learned electrostatics, right? Electrostatics was easy, right? We learned about Coulomb's law and then Gauss' law. And then as an subtopic of electrostatics, we learned how to solve Laplace equations, right? It's in a source-free region, like by using many different mechanisms. Like we used infinite series, and we also tried to do a image charge method. And then we start to learn about magnetostatics. So magnetostatics, currents are stationary. You have current, but the amount of current doesn't change as a function of time. And here we learned Ampere's law, and then Biot-Savart's law, right? And then what? And then we combine these two, and went on to this electrodynamics, right? So up to this point, the governing equations were very simple. Like in this case, the governing equation was this, right? And then here the governing equation was what? Like is there mu zero? Anyway, it's this simple. And now in electrodynamics, when things start to depend on time, we learned that this is actually proportional to dB dt, right? Which is Faraday's law. And then Ampere's law also needs to be modified. So it's not like simply a mu zero j, but you also need some dd dt term. Okay. The signs can be wrong here. I mean, I'm just talking about the essence, right? It's the signs, or there can be some coefficients I missed. But anyway, This is how it went. So we learned about, like, in electrodynamics, we learned like full Maxwell's equations. And with full Maxwell's equations, we jump onto electromagnetic waves, right? So we learned that Maxwell's equations can satisfy wave equation for the electric field and magnetic field, and then how the electromagnetic wave looks like it's when it propagates along this k direction, then electric field and magnetic field are perpendicular with each other, right? That's what we learned, and all this and how the electromagnetic wave propagates in a medium, lossless medium and lossy medium, and then what's the energy flow associated with electromagnetic wave. That's what we learned. And finally, we learned how the electromagnetic wave behaves at the material boundary, material interface, right? And here, in this part, what we do is, because we know the form of electromagnetic plane waves, we just assume those forms and then apply the boundary condition to obtain the relation between reflected wave, transmitted wave, and the incident wave, right? So that's it. That's what we learned throughout the course. And I hope you enjoyed this journey. And this is basically all I want to convey today. So if you have any question, please type in the chat box. Oh, okay. So Park Jun asks a question. So what he asks is why the forward propagation wave in medium 2 needs the e to the jk2d term multiplied. Okay, so yeah, so let's look at this. So here, so at this point, so it's important to understand at what exact position we evaluate the electric field. So here we evaluate at this point. At exactly this point, EI naught, and this is ER naught, and then this is ET naught, right? And then once you have a transmitted wave, you can write the transmitted wave like this, e to the T1 to EI naught, e to the minus j k2 plus r, right? This is a full form of this wave. And when this wave, when this wave was at r equals 0, 0, 0, that's tau 1 to EI naught. And now we want to evaluate this wave at this position, exact position, where r is 0, 0, L, right? The reason we do this is that we want to evaluate all these partial waves at exact same location, right? Otherwise, we cannot add. So in order to add these partial waves properly, we need to evaluate all these partial waves at the same position. And that same position is the origin here. And then in this case, the same position is the 0, 0, L. So even though I draw things in this manner as if X is increasing, but actually in order to add them properly, you need to evaluate all the partial waves at the same position, right? So we need to, so let's evaluate this at 0, 0, L then. Now, because K2 plus, and the angle between K2 plus and R is non-zero, right? Because K2 plus is going this way. So you have an angle. So this becomes K2 plus L cosine theta, right? So this term evaluates like that. And similarly, when this wave reflected back and then going back to the first interface, and in this case also we need to evaluate the electric field at the origin, not the position like a certain distance away from the interface, away from the origin, right? We need to evaluate things exactly at the origin for all the partial waves so that we can add them without any problem, right? So then once these two the wave travels twice, all you need to do is just multiply this by 2, right? And then the angle theta is taken into account by just introducing d. D is L cosine theta t, theta 2, right? I hope that explains the question. So what you need to understand is that all the reflected waves, even though I draw like this, should be evaluated at the origin, 0, 0, 0 position. Okay, and then all the reflected, all the transmitted wave should be evaluated at 0, 0, L. Okay, so and then you can probably understand why we need cosine theta terms. Okay, is there any other question? Okay, and Kim Jun Mo asks, why does when we add reflection and transmission, why doesn't this become 1? This is a really nice question. Let's just try to add, like, but the thing is, you cannot add gamma and tau like in just this manner, right? So what needs to be 1 is the transmittance plus reflectance, right? So let's say when you have a 1 boundary, then we know that gamma plus tau is 1. No, it's not gamma plus tau was 1. It's what was it? 1 plus gamma was tau, right? Due to the summation, due to the boundary conditions. But anyway, going back to Kim Jun-mo's question, what needs to be 1 is not the transmission coefficient and reflection coefficients. These are just coefficients, right? Doesn't necessarily be 1, added up to 1. What need to be 1 is transmittance plus reflectance. And then transmittance, reflectance can be written like this, but transmittance is a little more complicated because you need to take into account the Poynting vector ratio. And even when you add reflectance and transmittance, it's sometimes smaller than 1. Okay, it's smaller or equal to 1. The reason is if this material, the material sandwiched, has non-zero conductivity, so your epsilon is a complex number, then there is a loss. So you have non-zero absorption. And due to the energy conservation, what needs to be 1 is actually R plus T plus A, the absorption in the material. And that is always 1. Okay. So yeah, so that's the answer.